How are you? Right, let us look at integration over general regions. Right, I will draw a picture, and for now I'm just going to draw a picture. The question will say evaluate the double integral R at xy dy where R is drawn below. Now R is drawn below. I am giving you the drawing for now. Right, and this will be a drawing. Right, right, this is y is equals to 3, that is 3, this is 1:1, that is 5:3, and this equation here is going to be given as y is equals to negative 2x plus 3, and this equation there, it is y is equals to 1/2x plus 1/2, like that. So this is our region. We want to integrate there. Now, to do the integration at that point, we need to know the boundaries. So if I have a double integral 2xy, I need to have dd, right? I need to have these boundaries now. What are going to be those boundaries? What you need to remember is that this integral here, that integral must always have constants. So this integral here must always have constants, right? That is the y, that is the x, right? Because the last integral must always have constants, it means that this one must have constants or it must have functions. It does not matter, but the rule is that the last integral must always have constants. Now, I have a simple rule that everyone loves, right, when solving these. We do not complicate it. but we need to understand that a vertical line here means a dy, sorry, not a dy, a dx, and the horizontal line here means a dy. Do I understand that? A rule I'm having: a vertical line means a dy, a horizontal line means a vertical line means a dx, and a horizontal line means a dy. Now, where is this vertical and horizontal line is going to help us? It's going to help us to know I am ending with a dx or I am ending with a what? A dy. Right? It's going to help us there. Now, in what way? Because your integral must end with constants. Remember that the last integral is going with that one. We first need to discuss what will be your last differential. Now, how would you get that differential? A rule is, if you draw a line in a point of intersection, that line passes through the region we ignore it and focuses on that which does not pass through the region. Right. Now, you may fix the thing in here. I'm going to draw a simple region here. I'm going to get back to this problem. I'm trying to explain how would you get your thinking. Right. So let us draw a simple region. Let's say your region is in this form. Right. And your region, it is this one. That is your region. So these are the points of intersection of that region. This is the y, this is the x, right? Now that is your region. I'm removing the extra parts now. Now if that is your region, the rules say in the points of intersection, you need to draw lines. Now, what lines? It is this vertical and this horizontal line. This vertical and this horizontal. Right. Now let's start this A, B, C, D. Now let us draw a line, both vertical and horizontal. Now if we draw a vertical line, this vertical line is not inside this region, right? This one, it's A. This vertical line that I've just drawn is not inside this region, right? And then if you draw a horizontal line, it is also not inside the region. It means it's touching that line, right? Okay, let us go to D. It's also going to do that. The line D is also, it's only touching the region outside. But if you pay a close attention on B and C, when we draw a vertical line, that vertical line divides this original region into two regions. Do you understand that? When you draw a vertical line in B, it divides that region into two regions, right? So in this case, we say the vertical line is dx, right? In this case, when we come to this equation, we will not put a dx here. Why we are not putting a dx there? Because when we draw a vertical line there, it divides the region. But when we draw a horizontal line, it does not divide the region, right? Also, if you check here at C, draw your vertical line, it also divides the region. So we always try to ignore the division of a region. So when you draw a line, vertical or horizontal, and it turns out to divide a region, remember that the vertical line means dx, the horizontal line means dy, right? Because we have drawn a line at B, which is vertical, it means that here, at your last integral, you must not end with the dx because it divides the region. It means that for this particular region here, you need to end with the what? With the dy. If you pay close attention, a dy has a constant and a dy has a constant. It does not divide the region. Do you understand that? It does not divide the region. So that was the explanation on how to end with the dy dx, right? I'm also going to do it when we do other examples. Keep that in mind. I'm also going to do it. I'm also going to be explaining the same thing. Now, if you go to this region of mine, that is y is equal to 3. Just name this A, B, C. Right? Now, for A, B, C, what I'm just going to do, I'll try to draw lines in your region. Not this one. Black. Now, when we draw a vertical line at this point, does it enter this region? No. When we draw a horizontal line in this region, does it enter this region? No, it does not divide the region. Let's go to C. When we draw a vertical line like that, does this vertical line enter this region? No. When you draw a vertical line like a horizontal line like that, does it enter that region? No, right? With the same line, it does not. But when we come here at B, a vertical line divides the region. Do you understand that? That vertical line there divides that region. So if you draw a vertical line like that, you'll see that that vertical line that you draw at B, it's going to divide the region. Now it means for this particular region, you will not end with the dx, because a vertical line means you end with the dx, and the horizontal line means you end with a dy. Do you understand that? So I need to have a dy here. Because I have a dy here, I need to find what particular y value is here and what particular y value there. Now it turns out that particular values of y, it is 1 to what? To 3. Right, to 1 to 3. And the inner integral now is going to be dx. Since this inner integral is in terms of x, every equation that you see here which has a subject of the formula of y, you need to make you need to try to write them as in terms of x. So I'm going to have 3 minus y over 2 is equals to x for this particular equation. Right, and then I'm going to have a 2y minus 1 is equals to x for this particular equation. So how would you get these bounds? To get those bounds, it is very, very easy. You just draw a horizontal line starting from here to there. Now this graph in terms of x is what? It is 3 minus y all over 2. And then this graph in terms of x is going to be 2y minus 1. Now you can integrate that. Right. By integrating it, 1 and 3, remember we're going to integrate in terms of x, which means y is going to be the subject, is going to be a constant. So if I add the 1 and divide it by the 2, I'm actually going to get x squared y between 3 over 2 minus 1 over 2y, and then this is 2y minus 1. All of this is dy, right? And then I'm going to take this and substitute it in an integral between 1 and 3. Where there's an x, I'm going to substitute 2y minus 1 all squared times y minus y times 3 over 2 minus 1 over 2y all squared dy. Now you can just punch this to a calculator. It's going to give you a particular value of a, which is a constant. Always remember that this last integral must always have a constant, right? Let us look at the second one. The second one, R, I'm going to have xy dA for R is bounded by y is equals to the square root of x and y is equals to x cubed. Now I've given you the region in terms of equations. You need to know what equation are you dealing with. So let us draw that region. The most important thing here, it is the region, right? I know most of you don't know how to draw regions, but you need to draw this region anyway. So you need to draw it. So how would you draw this? Now, because there is a positive in the square root of x, it means that I am going to have a positive graph like that. And then that is an x cubed, and x cubed is a graph in this way. And they intersect at that point. This is your region. Now, We know that they intersect at 0 is to 0, but what is that point? To get that point, we need to equate the y's and solve for x. So I'm going to have the x cubed is equals to the square root of x. After this, I'm going to square both sides. I'm going to have x to the power 6 minus x is equals to 0, which is x in bracket x to the power of 5 minus 1 is equals to 0, where x is 0 or x is equals to 1. Now when x is equals to 1, when x is equals to 0, y is also is equals to 0, or when x is equals to 1, y is also equals to 1. So if you write them as a coordinate, you should have something like this, which is 0 is to 0. It is the point, it's the origin, and 1 is to 1. It is that one. So that one is 1 is to 1. Right. I think everyone is happy with the 1 is to 1. Right. Now, if you are given the equations, guys, always find the points of inflection. Whenever you're given the equations, always find the points of inflection. Now, let us do our thing. We go to the region, the points of intersection, we draw a vertical line. Is that vertical line passing through this region here? Does it pass through somewhere here? No, it does not. It's just a vertical line that they've just drawn, and then there is a horizontal line also. Is that that horizontal line, when you draw at the point of intersection, going somewhere here like that? No, it does not divide that region, right? So we are done with that point. Let us go to this point. When you draw a vertical line, it does not go through that point. When you draw a horizontal line, it also does not go through the region. Now, what does this mean? It means two things. Fibonacci's theorem, which means that an integral xy dx dy is actually going to be the integral xy dy dx, like that. So we can actually, if both of the lines does not go through the middle of this region, it means that you can write the integral in this form, but you can only solve one, because if you solve this one, you're going to have the same answer anyways. So let us first set up this one. How can you set up it? Now, because I am ending with dy, your minimum value of y, it is 0, and your maximum value of y, it is 1. And then to get these values here, I need to draw a horizontal line starting from this point to that point, this point to that point. Now, what is the name of this equation? The name of that equation is the square root of x, but I need to write it in terms of x here. Now, if you're writing it in terms of x, this one is going to be x is equals to y squared. So here I'm going to have y squared as your minimum function from left to right, from left to right, from left to right. And then your right function, it is that y is equals to x cubed. This one in terms of x is equals to x, the cubic root of y. So here I'm going to have the cubic root of y, like that. The main thing here, guys, is that I need to set up it for you. I will not show you the workings, but you need to know how to set up the equations, the integrals though. Right, let us look at this one. Now it's ending with dx. Now the minimum value of x, it is also 0, and your maximum value of x is also 1. And then to get these boundaries here, you need to draw a line vertical from the bottom to top, from the bottom to top. Ignore the horizontal line because the horizontal line only worked in this one. The vertical line that is drawn in a region is only working to this interval. So what is your minimum value of y here? It's going to be x cubed, and your maximum value of y is going to be the square root of x, like that, right? So you are going to integrate it for yourself, not me. This was number 1. Number 2, evaluate the double integral r x times 2 minus y cubed squared dA for R is the region bounded by y is equals to 0, x is equals to 0, and y is equals to 2 minus x squared, like that. So this is your problem. Evaluate the double integral x times 2 minus x cubed all squared dA for R is the region bounded by y is equals to 0, x is equals to 0, and y is equals to 2 minus x squared. Now if we draw that, by now you know this, that these two will represent, this one will represent the x-axis, this one will represent the y-axis. So whenever you see an equation y is equals to 0, it means that I'm representing the x-axis. You're going to draw a line in your x-axis. And when a line is saying x is equals to 0, I'm going to draw a vertical line on your y-axis. Right, so let us draw that region. Now your region, it is something like that, which is bounded by this axis and also bounded by this axis here. And then this point here, it is going to be a root 2 is to 0, and then that point there is going to be 0 is to 2, like that. So your region, this is your region I'm talking about. Now at all these corners, that corner and that corner, we should draw a horizontal line and a vertical line. Now if you can see, all of these lines are not inside the region. So it's going to mean the same thing. Let us set it up. X 2 minus y cubed all squared d like that. You can say it's dx dy, or x 2 minus y cubed all squared dy dx. But first let us start this one. Now when we end with y here, what do we mean? We mean that what is your minimum value of y in the x-axis, which is what? It is 0, and your maximum value of y, it is 2, right? You understand that one. And then for x, to get your value of x, you need to draw a horizontal line. You account for the start, you account for that start. So your x value will start at x is equals to 0, and this equation must be written in this form of y plus 2 is equals to x, and you have square roots there. So here I'm going to have the square root of y plus 2, right? Like that. And then if you write it in terms of y, it means that your last equation are constants, and your minimum value of x here and x there is going to be 0 and the root 2. And then for y, we draw a vertical line. This is your starting point, that is your end point. Your starting point for y is also 0, and your end point for y, it's going to be 2 minus the x squared. You see? Very, very easy. Very, very easy. But I know that you guys will try to confuse it among yourselves. There's nothing that I can do, but I know you will try to do that. You will try to confuse yourselves, but do not try to do that, guys. Do not try to do that. Now, let us look at this one. I'm only going to do the setup for you. Not going to do the math for you. You are responsible for your math. Now evaluate, yes, the double integral 2dA for r is bounded by x is equal to the cubic root of y, and y is equal to 0, comma x is equal to 2. Everyone can draw that. Everyone can draw that. So I have something like that. Now why is it curved? Alright, so here I'm going to have y, there I'm going to have an x like that. Now when we draw these graphs, now x is equals to cubic root is the same thing as y is equals to x cubed, because you cannot interpret this graph, guys. You cannot do that. And then you also been given the x-axis as also the boundary. So this is the type of graph that I'm going to have. I'm going to have this particular region here. That particular region. So at that particular region, this is 0:0. This here, it is 2:0, but I do not know the point of intersection. Now I want to get the y, but I know that the x-axis, it is 2. I'm going to say y is equals to 2 all cubed, which is equals to 8. So that point there, it is 2:8. So the vertical, if you draw a horizontal line there, it must touch y is equals to 8. Right? So this equation here, it is your y is equals to x cubed. This one is x is equals to 2. This one, it is y is equals to 0. So let us set up this equation. You are going to go to all 4 points, 2D, D like that. Now when you go to the 4 points, this one does not go to the region. This one also does not go through the region. This one does not go through the region. This one does not go through the region. This one does not go through the region. That one also does not go through the region. So it means that we can dx dy or dy dx. I'm just going to leave homework for you guys to find dy dx. So what are the boundaries then? Now if you say dx dy, what is your minimum value of y you have here? It is the x-axis, which is what? Y is equals to 0, and your maximum value of y, it is 8. Now to get your minimum value of x, you draw a horizontal line on that region from left to right. From left to right. Now what is this function in terms of x? In terms of x, it's going to be the cubic root of y, and the last one in terms of x is just going to be in terms is equals to 2. Right? So that is your work that you need to do. Turns out that I'm going to have an integral 2 times x between the cubic root of y 2 dy 0.8 4 minus 2 cubic root of y. Now at this point you can just plug this thing in your calculator. Just know that we do not want your calculations here. We want the setup and we want the answer. The calculations do not matter. Do not matter, really. They do not matter. So yeah. So the next thing that we need to do, it is the last one. The last one. It's not really the last one. But let me just split the video into 2. Yeah.